Ladies and gentlemen, welcome to the 2020 Zoom Olympics. Well, that was anticlimactic. Since they're here, let's meet our 4 contestants. The guy in the top right is Ashu, and this young fellow here is Sahas. He claims to be the master of virtual table tennis, but let's find out. We also have Jennifer, our track star, and Akhil, the biking extraordinaire. We will have 4 events today. We will start off in the depths of our backyard for a free throw contest, and then move on to a 400-meter neighborhood foot race. After that, we will gear up for some VR table tennis and finish it up with a 2-mile bike race in the hills. Let's jump right into event number 1, a free throw contest. Everyone gets 10 shots, and whoever scores the most wins. Ready, set, go.
Haha, these losers have no chance. I've been splashing shots every day in my front yard.
Welcome to my special move, my quadratic smash.
This is Ashu's last shot. Well, looks like Ashu made all his shots. How did you do it, Ashu?
Well, all it took was some calculus.
Now let's pretend this ring here on the paper is a basketball hoop, and this is our basketball. So if we go at this angle here, we can see that it's virtually impossible for the basketball to fit inside the hoop. But as we increase our angle, we see that there's more and more space for this basketball inside the hoop.
Now you might think that the ideal way to shoot a basketball is to get the highest arc possible, but that comes at a cost of energy. After a point, the player can't exert that much force on the basketball, or else they're just wasting too much energy for the rest of the game. So we need to find a way where we can minimize the player's force, but maximize the angle that the basketball comes into the hoop.
With the help of some physics equations, we can find the force required to get the ball into the hoop at a certain angle. In this example, we find that for a 60-degree shot angle, it requires about 4.73 newtons to get the ball in the hoop. We can do the same math for a bunch of other angles too, and if we plot all these points here, we can actually draw a pretty accurate curve to model the points. Using the tangent line with a slope of 0, at 45 degrees we find that we have a local minimum. But wait, there's another problem. We did these calculations assuming that the shooter's shot height is at the same height as the basketball hoop itself, which is about 10 feet. I'm tall, but I'm not 10 feet tall. So to account for my shot height of about 7 feet, we need to map down the trajectory of this about 3 feet down. If we measure the angle here, we get a final answer of about 52 degrees.
Wow, that flew right over my mind, but thanks for telling us anyway. Next up, our 4 contestants will compete for the best time in a 400-meter neighborhood foot race. There will be a timer on each of their 4 screens, and our high-tech AI system will stop the timer automatically when they cross the finish line. With that said, ready, set, go. Akhil's off to a great start here. Wow, look at Ashu go. If I didn't know better, I would ask him if he was Barry Allen. And what's this? Jennifer seems to be jogging right now. What's going on inside her mind?
According to Joseph Keller's theory of competitive running, the human body's physiological capacity for running can be measured with sets of simple differential equations. Runners must solve the differential equations to find the best pace for themselves at different parts of the race to achieve their quickest time overall. And this is what I'll be doing today. Keller's model predicts that for races under 291 meters, the optimum strategy is to sprint at 100% acceleration for the entirety of the race, which means you're sprinting as fast as you can for the whole race. However, for races longer than 291 meters, such as this one, the following equations must be used to optimize performance. The first equation here was derived from a model based on Newton's second law, and it's used to describe motion during the race. So this equation states that dv over dt plus v over tau is equal to f of t. In this equation, v is the runner's speed as a function of time, tau is a constant characterizing the resistance to running and is proportional to running speed, and f of t is the propulsive force per unit mass. The second equation relates propulsive force and energy supply. This equation states that dE over dt equals sigma minus f times v. So in this equation, E represents the runner's energy supply, which is restored at a constant rate sigma. In spite of this replenishment, the energy supply eventually reaches zero at the end of the race. So tau, sigma, E, and F are found by comparing optimal race times to the existing world records for 22 race distances ranging from 50 yards to 10,000 meters. Through solving these differential equations for myself, I arrived at this table for how fast I should be running during different parts of the race. As you can see here, at 50 meters, my time should be 9.03 seconds. At 100 meters, my time should be 18.30 seconds. At 150 meters, 28.57 seconds, and so on. So as you can see from this table, as the distance increment by 50 meters each time, my splits go up by almost the same amount of time also. So this means that I should be running at an almost even pace. With this table, now I can win the track race with ease.
As we get closer to end of our race, our contestants seem to be getting tired. However, Jennifer here seems to be approaching the finish line, and there she goes right across the finish line. Go Jennifer!
No! I lost! Whatever will I do? Oh well, better luck next time.
Nah bro, that wasn't luck, that was simply calculus.
Am I done yet?
No, you still have 50 meters. It's time for our next event, virtual reality table tennis. In the first round, we had Ashu with a sweeping victory on Akhil and Sahas beating Jennifer by a landslide. Now it's time for the finals, Sahas versus Ashu.
Man, Sahas thinks he's good at table tennis. We'll see about that.
Alright, let's get started.
It's time for the game to begin. Sahas serves first. Ready, set, go.
Pause. If I want to beat Ashu, I can't rely on my strength and charm alone. I'm going to have to employ some calculus. When playing table tennis, it's important to close the distance between you and your opponent. In this case, my optimal position would be the center of the table, so I'm as close to Ashu as possible. Assuming I'm moving at a constant speed of 112 centimeters per second, I want to find the rate at which the distance between me and Ashu is changing when I am halfway to the center of the table. The table is 152 centimeters wide and 274 centimeters long. If I were to make a diagram, it would look like this. By the Pythagorean theorem, the distance between me and Ashu can be represented by this equation. Now, differentiating with respect to t, we get this equation. 2d times dd over dt, which is the rate of change of distance, is equal to 2 times the quantity of 76 minus x times negative 1 times dx dt, which is the rate of change of my horizontal position, plus 0 for the constant. If we simplify that equation, we get the equation below. Now, when we're halfway to the center, the x value is 38. So if we plug in these values in our first equation, we get 276.622 centimeters. Now that we have the distance, we can plug in our known values into the second equation, thus getting negative 15.386 centimeters per second as our rate of change for distance. Therefore, when I'm halfway to the center of the table, the distance between me and my opponent is decreasing at a rate of about 15.386 centimeters per second. Hopefully, I'll be there in time to return my next shot.
After a grueling set, Sahas has come out as the victor. Ashu's long legs are no match for the power of related rates. Now let's move on to the final event, toward a mission. Contestants are to finish a lap of this course. That fastest lap time wins. Remember to wear a helmet, wear a mask, and most importantly, wear deodorant. Before we start, let's check in on some of our cyclists. Here we have Sahas. Sahas, what's your plan for the race?
Thanks for asking. I never skip leg day, so I plan on keeping my gear on 7 until I get to the finish line. That way I can be the fastest.
Interesting strategy. Let's see what Jennifer plans to do.
Biking is super easy. If I want to be number one, I gotta put my gear on 1. That's a winner's attitude.
Excellent and good luck. Akhil, what's your plan?
Me? I plan to use calculus.
Yeah, we know. Save it for after the race. Okay, everyone seems to be ready. On your marks, get set, go. We're only 10 seconds in and Sahas has a huge lead on the other participants. Looks like the high gear is working out. Meanwhile, Jennifer seems to have barely moved past the starting line. But slow and steady might pay off. Ashu and Akhil are almost side by side, ready to overtake the other. Ladies and gentlemen, this race will be legendary. And we're almost at the finish line. Looks like Ashu's in the lead after that downhill slope, but anything can happen.
Time for my calculus technique.
What was that? Looks like Akhil just switched his gear and is now in front.
Yeah, I won. Finally. It took me so long, but I did it.
And there it is, Akhil is the first to cross the finish line. I guess now's a good time to explain the calculus of biking.
The key to being the most efficient while biking is to keep your speed up while not overdoing it on energy use. To do this, you have to make the optimal gear choice while going on different slopes. The equation for efficiency is this. In this case, the motion of the bike is formulated as this. So m equals mass, c equals the coefficient of rolling distance, g equals the acceleration due to gravity, and a equals the acceleration of the bike. The energy output is formulated as the rotations per minute of the wheels. To find the most efficient gear, I plotted the efficiency values for each gear on every slope level. Afterwards, I estimated the curve using the points. Using the first derivative test, I could approximate the local maxima of each graph to find the gear resulting in the best efficiency. Switching gears throughout the race allowed me to win the end. For example, here's a graph of the efficiency of a 0.1 slope. As you can see, the local maximum of the graph is around 6, so the most efficient gear to take when you're going on a 0.1 slope would be 6. Another example is this graph of a 0.2 slope. The local maximum of this graph is at 2, so that would be the most efficient gear on this slope. Now, if Lance Armstrong used my technique, he might have not needed that little help.
Congratulations to all the participants. Remember to stay safe, stay healthy, and study calculus every day.